So hopefully you were able to figure out how to do this, but here it is if you did it, however you did it. So this is my tau of x expression. It's a function of, it's of order of mu, then u infinity minus 0, how much u changes, divided by delta, which we know is a function of x. So that's going to be my expression. And I'm going to, obviously use the thing we did in the last lecture, which is figure out the delta, delta explicitly as a function of x, put that right in here. So that's my formula for how tau changes with x in this problem. And you can see there's a u infinity in the numerator, u infinity in the denominator, there's a nu, there's, x in the denominator. So I'm going to crunch all these numbers. I'm going to put in some numbers. We said it's flow in air. So we're going to assume STP again. So we're going to assume T equals 20 degrees C, P equals 1 atmosphere. And that's going to allow us to look up nu. So nu is equal to, once again, 1.5 times 10 to the minus 5 meters squared per second. So 1.5 times 10 to the minus 5 meters squared per second for nu. And that's going to let us go ahead and plug numbers in for this delta expression. So delta of x is equal to 4.92. And I've got 1.5 times 10 to the minus 5 meters squared per second divided by 1.2 meters per second. That's our u infinity to the 1/2 power. And then that's all times x to the 1/2 power. So I get an actual number for this. So I'm going to go ahead and use that number when I crunch that with my calculator. So the number I got when I punched all that into my calculator is delta of x was equal to 0.0174, and then times x to the 1/2. This is actually comes out to the units of this are meters to the 1/2, and then I have x to the 1/2. So that's my expression for delta of x, and I'm going to plug that expression back into here, right? So I'm going to do that. So I have that. Yeah. So I guess if I wanted tau of x, that would be, u infinity, it'd be mu, u infinity over this 0.0174 times x to the 1/2. So that's fine. Now I need to put this into an integral. So the total drag is going to be the integral of that shear stress over the whole surface. So I'm going to have a double integral, 0 to L, 0 to W, tau, which is only a function of x. Then I have dz and dx. And that's my integral. And I'm going to multiply that by 2 because I have a top surface and a bottom surface. All right, so that's what I'm going to try to do that integral. Notice that tau is not a function of z. So we said this before, and it's still true. So it's not a function of z. So I can take that, it can pull that out of the z integral. So I'll do this very formally for you, just so you can see it. So from the internal integral, which is the z integral, tau is a constant in that direction. So I can literally pull it out. So I have 0 to w dz, and then dx, and this is still times 2. So this integral right here, that's just z evaluated at w and 0. So the f of the drag is equal to the integral from 0 to L of tau is a function of x. This integral, which is just dz, evaluated at w and 0, is just w, and then dx, and then that's all times 2. So I'm going to pull that w out. That doesn't need to be in there either, because w is not a function of x. So I can say that the total drag force is equal to w times the integral from 0 to L of this tau of x dx times 2. All right, so that's nice. So pretty simple. And now I'm going to, plug in my expression. As we said, tau of x, we have an expression for that. The tau of x we came up with was mu u infinity over 0.0174 times x to the 1/2. So that's my expression for tau as a function of x. So I'm going to put that in, right, to my integral. So F drag is equal to the integral W 0 to 0.7 of mu times u infinity over 0.0174 x to the 1/2, sorry, 1/2, this is 1/2, dx. I know mu and I know u infinity, right? Mu is, I can look mu up at standard temperature and pressure. It's 1.8 times 10 to the minus fifth Newton seconds per meter squared. And u infinity is equal to 1.2 meters per second because we said that earlier. So I'm going to put those numbers all in. And so I get that the total drag force is equal to, I should say approximately, because we are approximating the derivative here. W 0 to 0.7. Then I have those numbers that I've plugged in. So that comes out to be 2.16 times 10 to the minus 5. And that's newtons per meter, I think, times 1 over 0.0174 times x to the 1/2 dx. All right, so we can crunch these two numbers, this 0.174 divided by that. So you get that the total drag, this is still times 2. Sorry, I keep forgetting the times 2. This is times 2. We got two surfaces. So we've got that the drag is approximately equal to W times this integral from 0 to 0.7 of 0.00124. That's newtons per meter squared, I believe, times x to the minus 1/2 dx times 2. So we brought that x, just made it a negative exponent there. And then we have, this is just 2.16 to the minus 5 divided by 0.0174. So that's it, pretty easy. That's actually an easy integral to take. So, we had to do a little work to get here, but it's not a hard integral. It's just W, then the constant, 0.00124. And then I have 2 times x to the 1/2. So that's the integral evaluated at 0 and 0.7. So the integral of x to the negative 1/2 is just x to the 1/2 times 2. So that's easy. And of course, I'm still multiplying everything by 2 because I still have two surfaces. And so I end up that the drag force here is W 0.00248 because I multiplied 2 times 0.00124 times x to the 1/2 evaluated at 0 and 0.7 times 2. And so that I can plug in my 0.7 and take the square root, and I get W times 0.00207 times 2. And finally, I plug in my width, which was 3 meters, and I get that the drag force is of order 0.012. So I multiply this whole thing by 6, and that's my approximation for the drag force. So that's what I get as an engineering result using my scale analysis to evaluate the shear stress. This is in newtons. If you look at the exact answer for this problem, as determined essentially by using much more powerful mathematical techniques, you get 0.01 newtons. So we are very, very close, within 20% of the true solution, just using our scale analysis techniques. So I think this is a really good illustration, again, of just how powerful this is. And I'll emphasize again, we did this even at your level using pretty basic algebra and calculus from the full Navier-Stokes equations, those really complicated nonlinear equations. So it is a good example of how we, even if the equations are tough, under certain circumstances, we can use them to get really good results.